So I'm going to introduce Timo Ahonen. He's the Director of Engineering at Computer Engineering at Meta. He's got a pretty cool demo in front. And he has a wealth of experience that he's going to bring into this presentation. He hails from Finland, so of course he worked at Nokia, including here in the R&D group in Silicon Valley. And today he's going to be discussing quite an interesting topic of motion tracking for AR, VR, so augmented reality and virtual reality. Welcome.
My name is Timo Ahonen, and as David mentioned, I will be talking about Visual-Inertial tracking today. The aim is to keep this at relatively high level, so make this an accessible tutorial. So in order to give you all an insight or high-level overview of how to do ego motion estimation or position estimation for AR devices. And just to get an idea of everyone's background, can we do a quick show of hands? So who here has worked with inertial sensors, accelerometers, or gyroscopes before? Okay, so some people are familiar. How about geometric computer vision, stereo, structure from motion? Okay, so seems that we have some people who already are expert or have some background in this area. So I come from a company called Meta. We are an augmented reality company making software and hardware for AR. We are based here in Silicon Valley in San Mateo, and we relatively recently started selling our most recent product. This is the Meta 2 augmented reality headset, and kind of the rest of the presentation will be in the context of how to make the tracking work for a device like this. And on the headset, this is an optical see-through AR headset, meaning that the graphics are projected onto the visor, and the user sees the world around them directly through the visor. So it's not camera-based AR as in some other or in phone AR products. This is optical see-through. And when it comes to tracking, it's similar, but there are a few details that will work differently for a see-through as opposed to camera-based AR. So today's presentation will be divided into 5 parts. First, I will give an overview of why we want to do pose tracking for AR and what that actually means. Then we will look into inertial sensors, how you could use those to compute the headset poses, and why that is actually not a feasible option alone. Next, we will have a quick or an introduction to Visual Slam. There is also another presentation on Visual Slam today, so I will probably run through, even though there are a bunch of slides, I will try run through those relatively fast. You will all have access to the slides afterwards, though, so feel free to go back to the slides or reach out to me for any details. Once we have covered the inertial and visual part, then we will talk about sensor fusion and how to combine the two modalities. And lastly, we'll talk about how to apply all of this to augmented reality. So with that, let's get started. So this is what we aim to do. On the video in the lower right corner, you see a user wearing our Meta 2 headset. And what we want to do through computer vision and through the inertial sensors is to track the 3-dimensional pose of the headset. And this is what the user sees through the visor. So the user will see rendered content overlaid on top of the real world. Some of the content, such as the 3D mesh, that might be something that augments the existing reality. The rest of the content, such as the cubes, that might be just 3D models that is rendered, but we want to render such that it appears locked to the real world. And this is the key there. So the reason why we want to do 6 DOF pose tracking. I'll explain that in a moment. The reason we want to do that is to give the appearance that the rendered content, the models, the augmentations, that they are locked to the real world. That is the eventual goal we want to reach. So, as said, we want to track the 6 degree of freedom headset pose. And just to clarify what this 6 degrees of freedom means, so we have 3 degrees of freedom for translation. So the X translation, the Y translation, and the Z-axis translation. And then we have 3 degrees of freedom for rotations, so the yaw, the pitch, and the roll. So it is these 6 degrees of freedom that we want to track. Translation typically we typically just represent as a 3 vector. For orientation or rotation, things are a little more complex because orientations are, or rotations, the manifold is not Euclidean space, so things get a little more messy. Typically, we would use quaternions for representing the orientation. For those, I think I have 2 or 3 equations in today's presentation. I will use rotation matrix to represent rotations. So this is what we want to do. We want to track the device pose in the real world coordinates. And so how can we do that? And I already mentioned inertial sensors. That is obviously one way to get to the headset poses. And as we will soon see, those alone are not enough, though. So we need to add something else to constrain the poses from the inertial sensors. Typically for AR and VR, people use optical. That can be either inside-out type of tracking. So that would be what you see in VR products like Oculus Rift or HTC Vive, where you have either beacons or cameras put in the environment, and those are used to track the VR headset pose. What we do for Meta and what phone applications for augmented reality usually do is outside-in tracking, meaning that you have the cameras on the headset seeing the environment around them and using the environment representation to track the device pose. Also, you could use other modalities such as GPS, magnetic sensing, acoustic sensing, and so forth, but we won't talk about those today, though. So with that, let's first look at inertial sensors. How could we use inertial sensors to get the 6 degree of freedom headset poses? Largely thanks to the mobile and smartphone industry, today you can get a MEMS IMU inertial sensor for $1, give or take. That won't give you a very good IMU, but regardless, kind of that's the price range we are talking about. And these devices, what they will give you, or what this component gives you, is both translation and orientation related measurements. For the angular movement or motion, what the IMU measures, and this is important to keep in mind. So for the rotations, we measure the rotational velocity. That is what we get out. For the linear motion, we are able to measure acceleration. So we get linear acceleration and angular velocity. But unfortunately, things are not quite this simple. So given the true angular velocity, given the true linear acceleration in the world coordinates, let's see what we actually get out from the sensor. So for the angular velocity, we start with the true angular velocity. Unfortunately, the IMU devices, they exhibit bias, meaning that even when the IMU is sitting completely still, you don't get a zero reading. So there is some bias that the sensor has. And to make matters worse, the bias typically is temperature dependent. We will be able to calibrate for it, and a bit more on that in a moment. But the important point is that even with zero angular velocity, we get a non-zero reading. And then there is noise on top of the bias. So this is what we get for the angular velocity from the gyroscope. For the acceleration, again, we start with a true acceleration, but the accelerometer won't be able to distinguish between the gravitational force and the actual acceleration of the device. And this means that when the accelerometer is sitting completely still or is in constant linear motion, what the sensor outputs is upward acceleration with the value of gravity. So we can't tell, or the sensor cannot tell the difference between gravity and actual acceleration. Obviously, the sensor will measure the acceleration in its own frame of reference, or in its own coordinate frames. And that is different from the world-locked coordinate frame that we are interested in. So there is some rotation between the sensor coordinate frame and the world coordinate frame. And similarly, as for the gyroscope, there is the bias and there is the noise. So given these challenges, how can we or given this noisy outputs with bias, how could we get the poses, the 6 degree of freedom device pose based on these inputs? And this is a slightly simplified model, but still gives a pretty good idea of what is going on. So with the gyroscope, with the angular velocity measurements, we first need to estimate and subtract the bias. Practically how we do this is we often do already factory calibration to get an idea of what the temperature dependent bias is. So once we have estimated that, we subtract it from the gyro reading. Then, as mentioned, what we get from the gyro is the velocity. We want to get to orientation, so we need to integrate over time. And we're almost done. The only thing is that what we get at this point is the orientation in some random coordinate frame. And for AR applications, we want up to point up. So we want to have basically the content aligned with the real world up direction. And here, accelerometer and the fact that it actually measures gravity comes to help. So with accelerometer, again, we do the same thing, estimate and subtract bias. And now, as said, because the accelerometer measures not only the true acceleration, but also gravity, with this, or fusing this information with the data from the gyroscope, we can estimate which direction is up, or which direction is gravity. And now we have the orientation. We need to do a few more things before we have the position or translation. So first we want to rotate the accelerometer readings to world coordinates. So we were able to estimate the up direction, and now we want to rotate the accelerometer so that it's in world-oriented coordinate frame. Then we also were able to estimate the gravity magnitude. Now we need to subtract it from the accelerometer readings. And finally, we need to integrate twice to get the position. So this is a simplified model of how the estimation happens in reality, but these are the essential steps that happen behind the scenes to get the poses from the IMU. As I think you might be able to notice here, this won't work in practice, mainly because of this double integration here. So even if we have even a small, very brief moment of incorrect readings from the accelerometer, because of the double integration, that ends up having the system state in constant linear motion. And because of that, the translation or the position readings or the position estimates based on the IMU will drift. And the amount of drift depends on the IMU quality. For the consumer-grade quality IMUs that we have in devices like this or in mobile phones, this drift makes the IMU practically unusable for position estimation for longer periods than fraction of a second. We can estimate for a fraction of a second, though, and this will be important later on. But beyond that, it's not usable. For military and other kind of high-quality IMUs, we can, or it's possible to get much better results. But those IMUs are bulky and expensive, and definitely not usable for consumer-grade products. So. Just to recap, this model is simplified. In reality, we would use something like extended Kalman filter for the estimation. The benefits of this system or this approach are that the latency is very low and the frequency can be really high. So we can get readings from consumer-grade IMUs at, say, 1,000 hertz. So we get 1,000 acceleration and 1,000 angular velocity readings a second. And also, beyond the fact that the bias is temperature dependent, this IMUs are very robust to different motions and different environmental conditions. On the negative side, though, and I think I mentioned both of these already, but one big issue is this ambiguity between gravity and acceleration. Sure, we can try to estimate gravity and take it into account that way, but that won't be perfect. So there is some remaining ambiguity always. So that's one big issue. So the second problem is the drift that I already mentioned. So IMU alone for time periods longer than a fraction of a second, or with some of the new very advanced algorithms longer than a couple of seconds, this is not usable. So we need to constrain the poses. So we get poses from the IMU, but they drift. We need to find a way to constrain those poses to stop the drift. We have different options. We talked about magnetic, acoustic, GPS, but for our device, we decided to use inside-out slam tracking as the visual component to constrain the IMU poses. So this brings me to the second part of the third part of the presentation, introduction to Visual-Slam. So again, I won't be spending too much time on this, so that we leave some time for the fusion and applications. There is another talk on this later today, and if interested, I believe that there will be more detailed on Visual-Slam there. Visual-Slam, meaning simultaneous location and mapping, is a solution to the chicken and egg problem in computer vision, where assuming we knew the camera poses, we captured images of the environment in different camera poses, and assume we know those poses. Now it would be, and we knew the camera model, it would be relatively easy to create a 3D model of the environment. Similarly, if we knew what the environment is, and we didn't know the camera poses, but we had images from a known environment from different cameras. We could estimate the camera poses. Unfortunately, we know neither, so we need to solve for both of these simultaneously. We need to build a model of the environment while at the same time trying to figure out where the camera actually is relative to that unknown environment. I will mainly talk about monocular, so single camera SLAM today. In our headset and in some of the other AR systems, you actually have two cameras, and you can use stereo vision to further improve tracking. But until the end of this part, I will constrain, or I will just discuss monocular SLAM. Some of the major paradigms, if you are reading through SLAM literature, some of the major paradigms in SLAM include direct versus indirect methods. Direct means that the optimization procedure in the pose estimation uses pixel values directly and uses the photometric error as the error to minimize. Indirect, on the other hand, means that you first do some feature matching, feature extraction and feature matching, and then you use the geometric error, or the distance between the projected and actual feature as the error measure. So that's the first important two camps in SLAM. Dense versus sparse means if you use the whole image or only parts around some key points for matching. And lastly, filtering versus optimization means how you optimize for the pose. Filtering, typically different variants of Kalman filter, use a filtering approach, and in optimization you usually do bundle adjustment to optimize for the camera poses. Regardless of what the specific SLAM system or specific SLAM implementation you have you usually have these components in the system in one form or another. What is in behind and what connects everything is the map. So that is the representation of the world that the camera sees. On the top, we have the motion estimation. Usually, in a real implementation, this is one of the 2 or 3 threads in the implementation. So the motion estimation finds the features in the environment, and based on those features and comparing those features to the map, it then estimates the three-dimensional or 6 degree of freedom pose. The second component is the local mapping, and that is the part that tries, or that is optimizing the map. So based on what we have seen in the environment, what do we put to the map representing the world around us? But the map, especially in mobile applications where the user is wandering around, or robotic applications for that matter, the map can become really large. And because of that, we can't optimize the whole map all the time, and that's why we do it only locally for what we are seeing right now or what we have just recently seen. And then lastly, we also do need to do global map optimizations to solve for global drift, or if we find loops in the map, meaning that we come back to a location we have already been. So this is the third main component to a typical visual SLAM system. Next, I will talk briefly about the pose estimation, and pose estimation is used in actually all of these 3 components to the right, and these 3 just differ in terms of what you are actually optimizing for. In pose estimation, in optimization-based SLAM, you only optimize for the headset pose. In the local map optimization, you optimize for the headset or the camera pose, as well as the local key points. And lastly, in the global optimization, this is where you modify everything that you have in the map. And this would be your typical structure from motion problem for computer vision. So I expect that many people in the room are already familiar with this. Or actually, sorry, right now we're just talking about motion-only bundle adjustment, so not the full SFM. So for now, let's assume that that we have a model of the world. We know that there is a cube in front of us, and we know the real-world 3D coordinates. We know the XYZ coordinates of the 7 vertices of the cube we are seeing in front of us. We don't know the 3 camera poses, though. So what we need to do here is, given the 3D geometry of the world that we know, let's find the camera poses, and this is typically done through bundle adjustment or through minimization. And what we want to minimize is the reprojection error. So we know the camera projection model, and if we assume we know where in the real world the point is, and we make a guess of where the camera might be, we can project that point in the real world onto the image plane. Then we can detect the corresponding point in the image that we actually captured, and we just measure the Euclidean distance between where we expected to see the point and where the point was actually seen. So this is the reprojection error, and this is what we want to minimize here. So we want to find a camera pose such that it is that this sum of these reprojection errors is minimized. So this is the motion-only bundle adjustment. We assume we know the geometry of the world. We observe that world from different camera poses. We want to find out what the camera poses are. Now things get a little more complicated in the structure from motion problem. The difference between this and the previous one is that now we don't know the world geometry either. Through feature extraction and feature matching, we can tell that in all the cameras that this green point is the same point as seen here and as seen here. So we can match the points between the different cameras, but we don't know the world coordinates of where that point is in the world around us. So this is the core problem Visual-SLAM algorithm needs to solve for. What is the 3D geometry of the world around us, and where is the camera relative to that world? And I think I promised you 3 equations today. So this is 1 out of 3. So this is the bundle adjustment equation. I won't go into all the details of this, but what we want to do here is we want to find such camera poses and such 3D coordinates for these points, such that the reprojection error that I showed in a couple of slides back is minimized. This is what we aim to do. So now let's move to discuss SLAM specifically. So in SLAM we don't have multiple different cameras. We have the same camera in different positions. So we see the world from multiple poses as the camera moves over time. And in full SLAM, or in full structure from motion, we would actually try to find all of these camera poses and all of the 3D points around us. This very quickly becomes untractable. We might have the camera running at 60 frames per second, so there will soon be way too many camera poses to solve for. And this problem is solved in SLAM literature through using what is called keyframes or keyframe optimization. So from the history, we just forget most of the camera poses. We don't care about them, and the heuristics on which camera poses or which cameras to keep. Or which keyframes to keep is one of the key questions actually in getting Visual SLAM to work well. So this is one of the tricks we do to actually make the problem tractable. A problem we have now is, and I'm still talking about monocular single camera SLAM. So a problem we have is scale ambiguity. This means that think about the Hollywood effect. You can't tell if you are looking at a video of the Statue of Liberty at 100 meters away, or if you are looking at a miniature Statue of Liberty at 10 centimeters away. So from the cameras we get only angular constraints. But if we scale the whole system, if we make everything smaller or bigger, the angles will still remain the same. So from a single camera, monocular SLAM, we can only solve things up to scale. It could be that the point we saw was 10 meters away, and the camera moved 1 meter, or it could be that the point was 1 meter away and the camera moved 10 centimeters. So we can only solve things up to scale. This one way to solve this is, and I will talk about stereo SLAM very briefly here, is to add a second camera. And now when we have a second camera, here we have two monocular cameras, two monochrome cameras on the headset. When we calibrate this camera pair in the factory, now we have a metric constraint. We know what the metric distance between the cameras is. This is a fixed baseline, and as long as we see enough points in the world by both cameras, this metric constraint or fixed baseline will allow us to solve for the metric scale. And this would be added as another constraint to the equation. All right. So moving on. I mentioned before that so far we have assumed that we can actually tell or match the points seen by the camera in different poses. And this is a traditional computer vision problem: key point extraction and key point matching. So we want, first of all, we want to find for SLAM. We want to find good points that are easy to find from different camera poses, and maybe the most traditional computer vision algorithm for this is the Harris corners. These days, FAST is widely used for corner detection. But in the literature, you can find a bunch of different methods for finding corners or key points. Next, we want to be able to match them between the different camera views. And here, SIFT is a well-performing classical algorithm for key point matching. It's a little bit heavyweight or compute-intensive for real-time SLAM applications. So matching algorithms such as ORB that is a little bit newer are pretty widely used as well. But again, very traditional computer vision. So now that we have the basics covered, how does SLAM actually work? So for every frame that we receive from the camera, we assume that we have built some map already. We do some prediction, say using constant velocity motion model. We predict where we expect to see those map points that we saw in the previous frame, and we find matches in the current frame. If there are new points that we haven't seen before that would be good points to track, we add those to the list or to the map points. And now with these points and with the 3D map we have, now we estimate the camera pose using the motion-only bundle adjustment we discussed previously. And that gives us the latest camera pose. And we go back to step number 1. In a separate thread, typically, if that thread is done processing the latest frame, then we send this frame to the second thread, which does the map building or the map optimization, which can be either local or full bundle adjustment. So this is at the high level how a Visual SLAM works. Let's take a look at a couple of examples. OrbSLAM from University of Zaragoza is one of the top performing Visual SLAM algorithms with open source or with implementation available to the research and engineering community. OrbSLAM is indirect in that it uses the geometric distance between the key points and map points. It is sparse in that it uses only detected key points, and it is optimization-based SLAM system. It has three threads. The tracking thread is the high frame rate thread that is supposed to give poses at camera frame rate. And then in addition to that, it has two threads, the local mapping and loop closing, that run at a lower frequency that do the local and then the global optimizations to the map in the back. Because of use, as the name implies, OrbSLAM uses orb feature extractor or feature descriptor heavily for all the components. And because of this, it has advantages such that it is pretty robust to different illumination or different illuminations and other environmental factors. The downside is, and knowing that this is embedded vision conference, it is still, while it runs real time or at camera frame rate on a desktop or even laptop GPU, it might not be lightweight enough for an embedded application. So another method which is a little bit slightly newer from University of Zurich called semi-direct visual odometry. The authors claim this to be less than half or have less than half of the compute load of OrbSLAM while getting similar or even higher accuracy in the tracking. And major difference between this and OrbSLAM is that this is odometry only, meaning that it doesn't have loop closing. It treats the world basically as a never-ending corridor, and even if you come back to a place that you have seen before, SVO doesn't detect that. But even regardless, the accuracy is pretty high. And also for this one, the implementation is available. So to recap what we just discussed about Visual SLAM. For Visual SLAM, we have three main components: the motion estimation that actually processes the incoming frame and outputs the poses, and then we have separate components that in the background build the map of the real world based on what we have seen. So what are some of the pros and cons of Visual-SLAM? One advantage is that the drift is significantly lower than for IMUs. Visual-SLAM still drifts, especially monocular SLAM can drift quite a bit, but we are talking about a few percentage level drift, whereas IMU-based pose estimation can pretty much drift without bounds. Visual-SLAM can offer relocalization, so meaning that when you make a full circle and come back to a point where you started, we can recognize that place and we can close that loop, whereas IMU-based tracking obviously won't be able to do that. And lastly, we are building a map of the real world, and we can use that for other computer vision or human-computer interaction purposes. Visual-SLAM alone is not sufficient for augmented reality, not by a long shot though. So one major drawback is the latency. So a camera like this could be running at 60 FPS, 60 frames per second, for instance, meaning that we have 16 milliseconds between the frames to begin with. And then that combined with the processing time results in latencies that are not that might be fine for some robotic use cases, for instance, but are definitely not small enough for augmented reality. Also, the update frequency, 60 updates per second, tends to be a little too low for AR applications. Just like any computer vision algorithm, we have issues with sensitivity to environment, and I already talked about the scale ambiguity in case of monocular SLAM tracking. So, taking all of this into account, we noticed that actually inertial sensors provide information that is complementary to what we get from Visual-SLAM. And because of that, fusing the two different modalities actually looks pretty appealing. The two modalities provide complementary information, and because of that, from the sensor fusion theory, we know that because of that, the fused output should have lower or smaller errors than either of the inputs alone. We can do the sensor fusion at two different levels, and in visual-inertial tracking or visual-inertial odometry, these are usually called loosely coupled fusion and tightly coupled fusion. Loosely coupled treats the inertial and visual as two black boxes that provide pose outputs, and then we just fuse those poses. Tightly coupled fusion, on the other hand, does the information fusion at the sensor measurement level. So let's take a look at high-level architecture diagrams. So for the loosely coupled fusion, this is what the system would typically look like. And by the way, in AR applications or in AR products, both approaches are known to be used. So some of the products use loosely coupled fusion, some use tightly coupled fusion. So in loosely coupled, we have a separate inertial sensor-based pose estimation system. We looked at the details of this at the beginning of my presentation, and separate from that, we have the Visual-SLAM or visual motion estimation that we just discussed in detail. So both of these systems provide complementary position and orientation readings, and we do information fusion of those and get position and orientation with hopefully with smaller errors than either of the inputs alone. Tightly coupled, on the other hand, looks like this at the high level. So for the IMU, so for the accelerometer and gyroscope readings, we might do some pre-processing, but typically we just feed the velocity and angular velocity and acceleration measurements to the visual inertial motion estimation as such. For the visual part, we typically do feature detection and feature tracking as the pre-processing step, and now the motion estimation gets the tracks of the features as the input. And the visual inertial motion estimation then estimates the poses based on all of this information. So compared to some of the images I showed in the back, or a few slides back, in bundle adjustment based fusion, this is how visual inertial tracking might look like. So between the different poses, we not only have the observed map points as the constraints, but we have these inertial priors that we have measured with the IMU. So this is the third equation out of the three. So now in the bundle adjustment, we would add this as an additional prior, meaning that we want to find such camera pose that both the reprojection errors of the observed features are minimized, but at the same time such that the motion measured by the IMU is consistent with the motion that we would have measured between those two camera poses. So this is how the visual inertial fusion would look like in case of tight fusion with bundle adjustment. There are a number of very successful visual inertial tracking systems that use filtering, though, and I don't go into details of extended Kalman filtering or unscented Kalman filtering today, but those are the workhorses that power many of the filtering-based visual inertial SLAM systems today. One that is pretty widely used in the academic community anyway is called Rovio, and this comes from ETH Zurich. And as said, it is extended Kalman filter-based visual inertial tracking system. So for the Kalman filter, it represents the system state with the motion or pose and motion states. It also tracks the biases of the IMU, the extrinsics between the IMU and the camera, and then for the visual part, it tracks a number, typically 50 or so landmarks. And unlike any other method we have mentioned today, this is actually a direct method, meaning that it uses the photometric error between where we expect to see a feature and where it was actually seen. So this is not a geometric distance, but this is the photometric difference that is used by Rovio. Again, just like all the other methods I have mentioned today, the implementation of this is publicly available. All right, now moving on to the last part. So how to apply all of this to AR, and why to do visual inertial fusion for AR in the first place. And one reason obviously is that visual inertial helps us solve the scale ambiguity, but even more importantly, the inertial sensor allows us to get the latency down, and this is crucial for AR and also VR applications. So latency means when you have some rendered content on top of the real world or rendered content on the visor, when the user moves their head, when the when the rendered content seems to lag behind the real world. That is latency. In virtual reality, where you don't see the real world, it's a significant problem in that it makes the users nauseous. In AR, in see-through AR, that problem is slightly less because you still see the real world. So the nausea is less of a problem. It's still very bad user experience when the content kind of is swimming behind. And the cause of latency is, and actually we'll look at that in a little more detail in a moment. And well, how to solve it? One, be faster. Two, predict. So this is actually a pretty detailed slide or detailed diagram of what happens behind the scenes or why there is latency in AR applications. But what I want you to take home with you from this diagram is that when motion actually happens here, the content in the AR display is actually visible here. Time goes from left to right in this diagram. The time between the motion and when the photon goes out from the display, that is called the motion to photon latency, and we want to minimize that. That is the end goal. So what does this have to do with visual inertial tracking? One thing is now let's take a look at the sampling frequencies of the different modalities. These could be typical sampling frequencies of your camera and of your inertial sensor. So from the camera you get a new frame every 16 milliseconds or so. From the IMU you might get a new reading every 1 millisecond. That means that for every camera frame you have 16 IMU readings, and typically in the visual inertial motion estimation, the most convenient way to do this would be to just hold on to these 16 IMU readings and then process all of them when we actually get the visual information or the camera frame as well. That won't help us though. So we need to work on the visual inertial motion estimation so that we actually update or give update of the pose for every IMU sample that we receive, and this has two benefits. One, the IMU processing typically is much faster than visual processing, so the latency or the lag is smaller, and again we get much higher update frequency. Then every now and then we also get a new frame from the camera, and that's when we do this constraining the IMU-based pose that I spoke about previously. So we typically try to get new low latency poses based on the IMU out as quickly as we can, and then whenever we get data from the camera, then try to correct for whatever drift might have happened because of the IMU. So I mentioned in the very early part of today's talk that with IMU we can do position estimation for a fraction of a second, and this is now what I mean, that it's actually enough to do it for a fraction of a second, because then we get the low drift camera-based pose and can correct for whatever drift happened. So this way we can combine basically the best of the both worlds from the IMU and from the camera. Okay, and last slide for today. So what I spoke about until now is basically what we have done, what the community, the research community has achieved. There are still open challenges that remain. Some of the systems solve this better than others. I don't think anyone has solved this quite perfectly yet, though. So thinking of embedded vision again, the computational complexity is a big big issue still. So on one hand, working on algorithms with lower computational complexity is important, and also working on hardware implementations of part of this system to get a more power efficient system is another approach we can take. For AR, for augmented reality, jitter, meaning the kind of the small high frequency, small magnitude drift of the poses is a major issue. We can solve for that by doing essentially low pass filtering of the poses. The downside of that is that we'll increase latency. So figuring out that trade-off, or coming up with systems that have both low jitter and low latency, is still something that we are working on, especially given that we also have the computational limits. Scale and drift, as I already mentioned, and then getting the computer vision part to work reliably no matter what the environment is. So those are kind of more on the basics, or on the traditional side. Then looking into more into future, of course we want to also enable use cases where we have multiple users. We want to sell this to everybody anyway. So we want all the users to be able to localize and build a shared map. So collaborative mapping is another topic of interest. And finally, semantic SLAM, where we kind of not only find these mindless or these map points that we know nothing about, but we want to add semantics on those. So those are kind of some of the interesting problems we are working on these days. So you'll have the slides available after the conference. The last slide includes some further pointers. So if you're interested in learning more, these are kind of good papers and good open source SLAM algorithms to start with. Feel free to reach out to me. You can find me on LinkedIn. So if you have any questions or want to discuss more, feel free to reach out. So thank you.